Welcome to the next video, everybody. Today we're going to prove Criterion 2. This is the second of two criteria on isomorphisms of complete intersection rings. So let's recall the criterion and we'll get into it. Okay, so here's the criterion. Suppose that for each M positive, we have a commutative diagram of O algebras. You can think of O here as maybe some finite extension of ZP, the p-adic integers. And we want that diagram to look the following way. So we have O double bracket S1 through Sn. There's a map from that to R sub m. There's a map from that called phi sub m to T sub m. There are vertical maps from R sub m to R and T sub m to T. And then there's a surjective map phi from R to T. This diagram commutes. Okay. What else do we need to conclude? We need a surjection of O algebras from O double bracket x1 through xn to R sub m for each m. So I imagine O double bracket x1 through xm as living up top here, surjecting down onto R sub m. Okay. And then we also want these vertical arrows here to induce isomorphisms R sub m mod J0 R sub m with R and T sub m mod J0 T sub m with T, where recall that J0 is the ideal generated by S1 through Sn. Okay. And finally, we want T sub m mod J sub m T sub m to be finite flat over O double bracket S1 through Sn mod J sub m. What is J sub m here? J sub m is the ideal generated by what we called omega ms1 through omega msn, okay, where omega ms is the polynomial 1 plus s to the p to the m minus 1. So if you actually work that out, J0 is actually nothing but the ideal generated by S1 through Sn. Okay. The conclusion is that phi from R to T is an isomorphism of complete intersection rings over O, which is what we're after. So to prove this, we need a lemma. Let K be a field and let N be at least 1. And suppose we have K algebra maps, K double bracket S1 through Sn to K double bracket X1 through Xn. And then we want that to surject onto A via a map that we'll call F. And let's suppose that the K algebra A mod S1 through Sn, the ideal times A, has finite dimension D as a K vector space. Let's also assume that for some n large enough, specifically larger than n, little n to the n minus 1 d to the n, the induced map K double bracket S1 through Sn mod the ideal generated by S1 to the big nth power through S little n to the big nth power. We map from that via a map G to A mod the ideal, mod the same ideal basically times A. Okay, we want to assume that for some capital N large enough, this map here is injective. Okay, then F, this map here, induces an isomorphism of K algebras from this guy, mod the ideal generated by S1 through Sn, to this guy, mod that same ideal times A. Okay. The proof is fairly uninteresting in the sense that it's kind of just straightforward but tedious commutative algebra. If you want to work out the details, I don't think there's anything too enlightening there. You can see Cornell, Silverman, Stevens, page 353. Okay, so let's take that lemma for granted and let's move on to the next part. Okay. So a little setup. Returning to the setting of Criterion 2, we're going to let O be a complete Noetherian local ring with a residue field K of characteristic P positive. We'll let N be a natural number, and for M at least 0, let's let J sub M, as I said above, be the O double bracket S1 through Sn ideal, given by the ideal generated by omega sub M of S1 through omega sub M of Sn, where again, we recall that omega sub M of S is the polynomial 1 plus S to the P to the M minus 1. Okay, so same thing as it was above. Okay, so here's a corollary to the lemma. Suppose we have O algebra homomorphisms exactly as we had above. So O double bracket S1 through Sn to O double bracket X1 through Xn. That will map to A surjectively via F, where A mod, the ideal generated by S1 through Sn times A, is free of rank D positive as an O module. Okay, if for some M such that P to the M is greater than N to the N minus 1 times D to the N, the ring A mod J sub MA is a free O double bracket S1 through Sn mod J sub M module. Then the induced map, H we'll call it, from O double bracket X1 through Xn mod S1 through Sn to A mod S1 through Sn times A. So kind of the induced map we were considering above in the lemma, but brought kind of into this specific scenario that we're in after we mod out by this ideal generated by these variables. This induced map is an isomorphism of complete intersection rings over O. Okay. To prove this, you just need the lemma in this video that we just covered, and the lemma in the previous video. I believe it was in the previous video. Okay, so see if you can. Okay, here, I'll just say this. Watch the past like 2 to 3 videos. The most recent lemma in those videos and the lemma in this video together give you this immediately. So I'll leave that as an exercise. Okay, so let's prove criterion 2. That's pretty easy now, actually. So let D denote the O rank of T. So T is this guy down here. Okay, so D is going to be the O rank of that. And now let's let M be large enough such that P to the M is bigger than N to the N minus 1 D to the N. By hypothesis 1 of criterion 2, okay, hypothesis 1 is the surjection of O algebras from O double bracket x1 through xn into R sub m. Okay, what did we learn? There's a surjection from O double bracket x1 through xn to R sub m. Okay, we're gonna focus on this specific M. Okay, let's lift the homomorphism that we were given from O double bracket S1 through Sn to Rm to an O algebra homomorphism from O double bracket S1 through Sn to O double bracket X1 through Xn. So the way I'm thinking of it is like, we've got this map here, okay? And then we've got O double bracket X1 through Xn surjecting onto R sub m, and I want to lift, okay? So lift it. Apply the above corollary now with A equals T sub m. So T sub m lives up here. Okay, so here is the situation we're going to apply the corollary to, because all the criterion are satisfied. Okay, what do you conclude? Well, you conclude that the composition O double bracket x1 through xn mod the ideal generated by s1 through sn, which surjects onto R sub m mod ideal generated by s1 through sn times R sub m, which surjects onto T sub m mod ideal generated by s1 through sn T sub m. That has to be an isomorphism of complete intersection rings by the corollary. Okay, but by the final kind of like slew of properties from criterion 2, so this stuff up here where you have these isomorphisms, okay, what you're given, that isomorphism we just found, actually is just going to end up being an isomorphism. Phi is going to end up being an isomorphism from R to T because these guys are isomorphic essentially, if that makes sense. Okay, so you're kind of exactly using the criterion needed, the hypotheses in the setup of criterion 2 to conclude. Okay, so by the final property of criterion 2, you have an isomorphism of complete intersection rings over O, and that's that. So this was a little bit briefer than criterion 1. A lot of the work was buried kind of in this lemma up here that I didn't prove, but I kind of just, I promise you it's really just some commutative algebra. I'm not saying it's like super easy or anything, but I'm not going through proofs unless they're like, I don't know, unless there's something kind of like enlightening, particularly enlightening in there. Okay, but head over to Cornell, Silverman, Stevens and check all that stuff out. Okay, so I believe we're going to start getting into the proof that R equals T, which is kind of the big thing that you have to prove Fermat's last theorem. I think we're going to start getting into that in the next video. So I'll see you all then. Thanks for watching.